In this video, we'll demonstrate how to compute the optimal or maximum speedup that can be obtained given characteristics of the programs that we're developing and the number of processors that we're using. I'll start off with just a little bit of review from last time, where we had the idea that we would record the number of processing units we're using as n, the amount of time it takes to run a program in serial on one processor as t serial, and the amount of time it takes to run in a parallel processing setup as t parallel. We saw that the time to perform parallel processing of a program should be the time to perform the processing on one processor divided by the number of processors we're using, assuming that we've evenly distributed up the work, plus the time to do some overhead, so communication costs, coordination costs, kind of dealing with the fact that each chunk of the data may not be able to be processed completely independently. We saw a definition for speedup as the time serial versus the time parallel. So if it took 8 seconds to run it in serial and 2 seconds to run it in parallel, then we had a speedup of 4. And then efficiency is speedup divided by the number of processors that we have. So this P should be an N as well. I'll fix that. And this gave us a measure of kind of what are we paying in terms of gaining that speed up. So is it an efficient use of the processors? If we have low efficiency, we're using a lot of processors and not gaining much from it. So what I'm interested in getting across this time is this idea that the amount of a program that can be parallelized then constrains the speedups that we can achieve, right? Regardless of how many processing units we have. So we're going to look at a program and say, okay, this piece has to be run in serial. There's something specific that says I have to do this with one processor. I can't break up the work. Then we'll assume some other chunk can be broken up. And it's that proportion of how much must be done in serial versus can be done in parallel, which will allow us to basically figure out how much speedup can we actually get. If a lot of our program can be parallelized, we can get high speedups. If not much of our program can be parallelized, we're not going to get a large speedup at all, regardless of how many processing units we use. So here's the setup. Assume that some portion of our programs can be parallelized, say k%, while the other portion, 100 minus k%, is due to some constraint inherently non-parallelizable. And in all of these slides and in the practice problems you do, we'll write k as a fraction of 1. So 10% parallelizable is 0.1. What we're also going to do, since we're talking about the maximum speedup we can obtain, is we're going to say that this k% that we're parallelizing is perfectly parallelizable, so we don't have to deal with any overhead at all. So that's really not true in the real world, but it does allow us to compute a maximum speedup. Under this notion that, well, we don't have to do any overhead, so we're just divvying up the work and seeing how we perform. So if we know that k% of a program is parallelizable and the other portion, 100 minus k%, is not, we can think about the parallel running time in this sense. That the time for parallel should be the proportion that can be run in parallel times the amount of time it would have taken in serial divided by n plus 1 minus the proportion that can be run in parallel times the time serial. So the way to think about it is this is the work that has to be done in serial. So if that's 10% of our program, then we're going to record, well, what fraction of the serial time are we going to have to use even when we're running it in parallel. And then this is the proportion that can be run in parallel. So it is whatever that proportion is times the time it would have taken in serial divided by the number of processors, right? So we're counting for the time it takes to run the parallel part, the time it takes to run the inherently serial part, and those added together are the total parallel time that we'll see. All right, so let's look at this and what it can tell us. So first, I'll just start off with an example. If a program takes 20 seconds to run in serial with one processor and is 90% parallelizable, and we want to parallelize with n processors. Well, so for the 90% that's parallelizable, using the formula on the previous page, which is this idea called Amdah'ls Law, we know the runtime of the parallel part is the 90% of it, given with the original serial time, but divided by the n processors. Since our original serial time was 20 seconds, it's 0.9 times 20 over n, or 18 over n. So this says, of the original 20 seconds it took to run with one processor, since 90% is parallelizable, that 18 seconds we can decrease and say those 18 seconds, that 90% we were doing that's now parallelizable, I can reduce it by throwing some n processors at it. So the larger n gets, the smaller this contribution to the cost should be. If n is 1, it's going to contribute the original 18. If n is 2, it's going to contribute 9, and so forth. Then the runtime of the serial part is just the part that must be run in serial, the 10% for this example, times the serial cost. Since our serial cost was 20 seconds, we're basically saying at least 2 seconds of our program are going to be used for the serial part, so our program has to take at least 2 seconds, plus whatever amount of time it takes to run the parallel part. All right, so let's see what that says. It says, for this program, under these constraints, we can compute the parallel runtime as t parallel is 18 over n plus 2. So then what I want to show you is I plugged in different numbers of processors, basically various powers of 2. I computed t parallel. You see that it does decrease. I'm just plugging into the formula. With 2 processors, 18 over 2 plus 2, which is 9 plus 2 is 11. 4 processors is 18 over 4, that's the parallel part, becomes 4.5, plus 2, the serial part, so it's 6.5. It decreases as we increase the number of processors, time parallel. And we can see the speed up. So this is the time serial, 20, divided by the time parallel that I just computed. And we get speed ups of 1.82, 3.08, 4.71, and so forth. Right, so what I did is I just, given those problem constraints, I set up a way to compute t parallel for various numbers of processors, and then I computed the speed up after I knew t parallel, and since I already knew t serial 20. Right, if you look at this, you can probably see 2 things. As we increase the number of processors, where our time parallel is asymptotically moving towards the value 2. Why is that? Well, remember that 2 is the amount of time it takes to run the inherently serial part of the program. So 2 is the smallest amount of work or amount of time required, because we just have to have that for the serial part. And then we could maybe get a little extra time if we had lots and lots of processors over that. Right, so at best we can reach a t parallel of just over 2. That also says that the best speed up we can get is going to be 20 over 2, which is approximately 10. So we should be asymptotically moving towards 10 as our speed up. This might be easier to think about in a picture. So what I did is I graphed the number of processors versus the speed up we should be able to achieve. And you'll see that we are asymptotically reaching the value 10 as our maximum speed up for this problem. I think there's several things we could think about from this. Maybe it suggests that once you go past about 256 processors, it's not worth adding more processors into the mix or using more processors to solve the problem, because you're just not going to be able to eke out much more of a speed up. All right. So this just kind of continues the idea. We know speed up is T serial over T parallel. We know that T parallel under this model is the fraction that's parallelizable times the time it takes to run the program in serial divided by the number of processors plus the time it takes to run this inherently serial part. We can think with an infinite number of processors, so if n is infinitely large, then this component of T parallel goes away. T parallel is then minimized if this is gone, right? Because we've taken away a part of the sum. So if T parallel is minimized, then S will be maximized. Having a minimal value here gives you a maximal value for S. Just plugging and playing from this screen to here, we know the maximum speed up is T serial over 1 minus K T serial. And I reduce that even further to basically say, with an infinite number of processors, the maximum speed up is inversely related to the percentage of the program that's not parallelizable. So speed up max is 1 over 1 minus K. All right, so if 60% of the work is parallelizable, can we just use this formula to plug and play for the maximum speed up? Yes. So we take 60% of the work is parallelizable. So K is 0.6. So under this formula and this percentage of work that's parallelizable, the maximum speed up is 2.5. How about when 90% of the work was parallelizable? It's 1 over 1 minus 0.9, which is 1 over 0.1, which is 10, which is exactly the maximum speed up we saw in this graph. Right, so one last idea. We know how to compute the maximum speed up, assuming an infinite number of processors. We can also compute it for a fixed number of processors. And again, what I'm going to do here is I'm just going to basically derive or rewrite the formulas so we get something fairly easy to work with. So if we want to compute the maximum speed up for a program that's K% parallelizable using a specific number of processors N, we can start with the formula for speed up. We know what T parallel is based on our proportion that's parallelizable and proportion that is inherently serial. So we'll plug in the formula for T parallel in the speed up formula. We'll obtain this formula. And then if we think about extracting out T serial, because this T serial can be factored out of the bottom, and then the T serial, because it's multiplied into both bottom parts of the sum, then the T serial factored out of the bottom will cancel with the T serial on top, saying the maximum speed up within processors in a program that is K% parallelizable should be whatever this formula reduces to, which is 1 over Kn plus 1 minus K. So let's see an example of that in use. What's the maximum speed up for a program that's 90% parallelizable with 4 processors? Well, we know it has to be less than 10 because that's the maximum speed up for this, for something that's 90% parallelizable with infinite number of processors. I'm just going to plug into the formula from the previous page. It's 1 over K over N plus 1 minus K. K is 0.9 in this example. N is 4 in this example. So it's 1 over 0.9 divided by 4 plus 1 minus 0.9. And this reduces to 1 over 0.325, which is 3.08. Alright, that was a lot of formulas and ideas. But what I wanted to get across is we're going to be running our programs, recording the timings that they take, and saying, given my implementation, given the coordination and the communication required between processors, what speedup and efficiency am I attaining? What the slides for today show you is what's the maximum speedup you should be able to obtain given some characteristics of your programs. And what we did is we looked at two things. We said, under an assumption that we can perfectly parallelize everything, so there's no coordination communication costs, and I have an infinite number of processors, what's the maximum speedup I can obtain? There's no way to get better than that. And then given perfect parallelization, no coordination, no communication, some percentage of the program being parallelizable and a fixed number of processors, what's the maximum speedup I can obtain? Right? And what this Amdah'ls Law will allow us to do is allow us to say, how am I performing, given my implementation, to what I should be able to perform in kind of a perfect world. So what you can expect is a few problems that ask you to kind of set up and compute the maximum speedup under different conditions. Right? That's it. Thanks.